Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Maths 3, iterations and vectors. Now remember I put them together in the same unit because they don't really belong with anything else or they don't join well with other topics. So I put them together in one unit. We already covered iterations in part 1. Now we're moving on to vectors. And here in our part 2 for this unit, we're now getting to vectors and we're going to look at magnitude and 3D vectors. Now let me take a moment just to explain what has happened in the syllabus change. In the old syllabus, there was a section of vectors in Pure Maths 1 and a section of vectors in Pure Maths 3. What they have done in the new syllabus, now starting 2020, is they have completely removed the section of vectors from Pure Maths 1, taken all of it, they've taken half of what was in Pure Maths 3 and put it together in Pure Maths 3. So the other half they got rid of. So if you're looking at old past papers and you see questions about planes, that's the part that they've gotten rid of moving forward into the 2020 syllabus cycle. The other half of P3, which is three-dimensional lines, they've joined with the P1 material and put it all together, but they've kept it in the P3 book. So if you see some of the question examples that I use, you might notice that the code goes back to Pure Maths 1. Don't worry about it. That's because all of that material is now in Pure Maths 3. So just to let you know about the syllabus change. Now, what we want to do is kind of have a little bit of review. I'm sure you've already had an introduction to vectors, probably in the IGCSE material. So we just want to review a little bit about notation and some terminology, and then we'll jump into magnitude and three-dimensional vector diagrams. So remember what composes a vector. There's two components to a vector. One is magnitude, which is a scalar value. It's kind of how much. And then there is direction. And so magnitude can be distance, if you're dealing with kind of like on paper, the length or distance between points is magnitude. You also see magnitude in physics type questions, such as the force has both magnitude and direction. Also, you see in like velocity is a vector. Speed is the magnitude, that's the scalar part of it. And then when you give speed a direction, it becomes a vector quantity. It now becomes a velocity. So vectors are quite useful, especially in a physics math application. But we also want to cover the mathematical part of vectors. And so this is our first of the vector videos in this unit, and we will have several videos going through the different vector skills. Another thing I should also mention is that the vector question type actually has a pretty broad scope in the type of questions that it asks. Some of those outer edge scope questions deal with some geometric things like area of a triangle, or show that something is an isosceles triangle, or with trapeziums. So what we're going to focus on is the core part of the vector scope for two reasons. One is it's what's directly related to vectors and vector skill sets. And also it happens to be the more frequent of the question type as well. So some of that outer fringe, you might notice some things show up in the vector questions that we don't cover, but they should be related to geometric skills that you then integrate with what you've learned about vectors. So we're going to focus on the main vector skill sets that you need to answer the vector question types. So let's first look at how to notate a vector. Now, maybe in IGCSE, you're a little bit more familiar with two-dimensional vectors. Now you got to get used to three-dimensional vectors. And so instead of just an X and Y axis, you now have an X, Y, and Z axis. So there are two basic forms that you're going to work with. And also the question types will present the material in these two basic forms. One is called component form, in which it uses I, J, and K to represent the X, Y, and Z axis. I and J and K are referred to as unit vectors. Now we're going to discuss how to find a unit vector in a following video. But for right now, all you need to know is that a unit vector has a magnitude of 1. So I is a length of 1 along the x-axis, J is a length of 1 along the y-axis, and K is a length of 1 along the z-axis. So I, J, and K are basically the same thing as your x, y, and z axis, but they are unit vectors, lengths of 1, and the A, B, and C are the coefficients telling you how many lengths of 1 that you need to go in that particular direction. Right? So again, if you see the question give you information in component form, then you should probably put your answer in component form. If you see the question present the information in column vector form, then give your answer in column vector form. So column vector, basically the same thing, except you don't need the I, J, and K. You just take the A, B, and C and you put it into this column, and it's referred to as a column vector. And another thing that's important is this can also be referred to as direction. So when you get into three-dimensional vectors, you want to use the term direction, meaning how to get from point A to point B. Try to not call it slope. You're used to slope in two-dimensional vectors. And while there are some similarities between direction and slope, there are also some differences. So if you're working in two-dimension and you have change in y over change in x, then you can call it slope. But when you're working with three-dimensional vectors, you want to refer to it as direction, although you will see similarities. So this is the direction of how to get from point A to point B. And this is same thing, but going along the x-axis and then the y-axis and then the z-axis, I, J, and K, still shows you how to get from A to B. So this is component form. This is column vector form. Personally, you're going to see that I like to use column vector form because it's a little easier to use with math than the component form. Although I will use both, and so it kind of depends on the context. Sometimes you can take information in component form, switch it to column vector form so that you can do math operations, and then you can switch it back into component form for your final answer if the original information was given in component form in the first place. Okay, so put your answer in the same form as the information provided, but you have two different forms that you can work with. If you're working in component form, you're working with it kind of like algebra, where you combine like terms. And if you work in column vector form, hopefully you're used to that from IGCSE material. Okay, then we also have what's called the position vector. The position vector can take a column vector, those A, B, C, and it can write it out as a coordinate. In other words, these are where you're at from the origin. Position vector means you're coming from the origin. It can also be written as a column vector, but position vector is a little more specific because you're at the origin. If you're not at the origin, then you need to write it like this. You can't write it as a coordinate. You write it in the column vector form if you're not starting from the origin. So when you see this OA and it's given in column vector form, or if it just uses the terminology position vector, you need to understand that it's the OA or origin to some point. Okay, so these are the main terminology and notations that you need to be familiar with. Also, the negative direction. Don't forget when you're going backwards along a vector, it changes the sign of the vector. So B to A is actually a negative of A to B. And that's an important thing to remember, especially when we get into the dot product. The two directions, they are different directions, even though the numbers in the column vector, the numeric part will be the same, but the sign will be different. So if you're going backwards on the x-axis, that would be negative I. If you're going out from the board on the J or the y-axis, it's negative J. If you're going down, that's negative K. So keep your direction in mind. It's important with that. Okay, so let's look at finding the magnitude of a vector. So the magnitude part has to deal with, in our types of questions with the Cambridge, it's going to deal more with the length. Okay, so remember, magnitude can be force, and physics can also be the speed part of velocity. So you have to find the context for it. So when we're drawing out on paper, then magnitude basically becomes the distance between the 2 points. So if we're finding magnitude of AB, it would be designated like this. Looks like absolute value signs, also kind of looks like matrix symbol. So you really need to know your context when you see these symbols. In this case, it's referring to magnitude of this vector AB. And since it's distance, it just follows your distance formula where you have the square root of, and then you have your A, B, and C. It's the same thing in 2-dimension as it is in 3-dimension, except you just have the additional number. So it's A squared plus the B squared, and when you get into 3-dimensional, you now have the plus C squared. So you take your column vector or the coefficients of your component form, and you square each of them, add them together, and then take the square root. Remember, square roots do not distribute across addition, so make sure you do the inside first before you do the square root part. This is how you find the magnitude. Now, Cambridge questions, especially in A level, they're probably not going to ask you specifically to find the magnitude. However, this skill is important for you to carry out various other questions where the magnitude is one skill that you have to use within that question. Okay, so that's kind of the basics. Now let's look at our first application, I guess, and we want to look at some 3D diagrams. So let me set up for the first of those. Okay, let's look at our first question together. And so here we go. Remember that these, the code on here is S19 from paper 11, meaning it's coming from Pure Maths 1. But this material has actually now, for the 2020 syllabus, is now actually in the Pure Maths 3. So don't get confused when you're looking at past papers. Also remember that anything to do with planes has been eliminated from the old syllabus going into the new syllabus. Here we have a three-dimensional diagram, and it says the diagram shows three-dimensional shape in which the OABC and the upper one DEFG are identical horizontal squares. Parallelograms, OAED, OAED, that's the front face, and the DEF or the CBFG, that's the back of it, the front face and the back, both lie in vertical planes. The point M is the midpoint of AF. So M is the midpoint of this diagonal A to F. So that's important to know. The unit vectors I, J, and K are parallel to OA, OC respectively, or the I and J part. K is not parallel here. It's its own axis, but I and J are parallel to this square. And unit K is vertically upwards. The position vectors A and D are given by OA is 8I, so it means it's 8 I lengths long, and I is 1, so that means this is 8 here, and this is a square, meaning we have 8, 8, 8, and 8, both in the bottom as well as in the top. As far as lengths, OD is 3I plus 10K. So 3I plus 10K means that our vertical height here goes up to 10. So that's where we need for that information. And it's also leaning, so it leans into this 3 units, but the height is 10. So express each of the vectors AM and GM in terms of I, J, and K. So that's what we want to practice in this video, is getting your 3D vector correct, because as you move forward, you're then going to use those in what's called the scalar product or dot product formula. So here is your MG, M is the middle, so MG and MA, or GM and AM can go inside or out. And here's AM and GM. So if you get this first part wrong, these questions are linked, and so you're going to end up getting the second part wrong. So make sure you take your time. You got 3 points, so it's roughly about 5 minutes of time. And look very carefully at your diagram, read the information carefully, but go ahead and take all 5 minutes. You want to check and double check to make sure your vectors are correct, because you're going to use those in the following parts of the question. So let's go to the board here, and I apologize because my 3-dimensional drawing is not really that great, but it allows me to draw on here, and I'm more comfortable drawing on the board than trying to do it in the video or on in the screen there. So what it's asking for us is to find from A to M. Remember, we're providing directions on how to get from one to the other. So we want to go from A here, and we want to come up to how to get up here to M, from A to M. So what you want to do is you want to go through each axis separately. Don't try to do it all at once. Look at each axis separately. So along the I-axis, how far am I going out in this direction in order to get from A to M? Well, remember your A is already lined up here directly with the origin, but this diagram has been tilted in, and it's been tilted in 3 units. Because remember, from O to D was 3I, so that means over 3 and up 10, over 3 up 10. So from the vertical, this is 3 units over. So here we have 0 to A, and then this other side has also been tilted over. These are parallel sides here. It's been tilted over. So it's not directly on the vertical here. And so if we draw the vertical up, this is three units. These three got shifted over. And this is the midpoint. So the midpoint means it's going to be not all the way pushed over as the top is. It's only going to be pushed over halfway. So from A coming out here to where the M is lined up, this is going to be 3 halves. 3 halves on the I-axis, because it's half of this 3. We're down in the middle of the graph here. We're down here at the middle part. So what we want to put here is 3 halves I. It's not how far you are from the origin, it's how far you are from A. Going from A to M, we have to come out 3 halves on the I-axis. Then you want to look at the J-axis. The J-axis, this is going straight along, and this is also following the same path. It has 8 units long. M, again, is the midpoint. So we're going to go into the board 4 units. Again, because it's midpoint, it's halfway. So plus 4J. And the height of this whole diagram is 10. And again, because it's the midpoint of this diagonal, means it's also halfway up the height. So we have to go up 5 units. So 5K. Okay? So 3 halves I in the I direction, 4 in the J direction, and 5 in the K direction. Now we want to look at from G to M. Here's G, here's M. So going that way. Make sure you know which direction you're going. We're going from G to M. And so now again, you want to look at the I value. Now from G to F is 8 units. Okay. From G to F is 8 units because it's a square just like the bottom. But M is recessed in from the F. Remember, this is like this. So F is at 8. Here, G is right along the J. So this 8 is still 8, even in the back, the front and the back, it's still 8 because it's along this J axis here. 8 going out I, 8 going out I. So this is 8 going across, but it's recessed back the 3 halves, this 3 halves here. So what we want to do is we want to take 8 minus 3 halves, that's 16 halves minus 3 halves, which is 13 halves. So we want to take our 13 halves I. That's how far it is from G over to M on this. So it's kind of like 8 and then back 3 halves. This is what lines up with the M. 8 is the total minus the 3 halves. So that's the 13 halves. Then as far as the J, this was all the way in on the J. And now we want to come back halfway. Okay, G is all the way in, it's all the way at 8, and we want to come back half of that. So this is going to be minus 4J because the direction is back out of the board or out from the back of the diagram. And we want to go down on the Z-axis, again, half of the height of the diagram. This is at the top of the diagram, M is in the middle, so we want to go down 5K. So take your time, really think it through. It's important you get the right values here, not only so you can get the points for this part, but because it carries over into the next part, it's usually linked to what you do next. And if you get this wrong, you'll get the next part wrong and lose double points. So this is how you find the vector values or your direction on a 3D diagram. Here, I'll set up for another one. Okay, let's go on to our second diagram, and I'll show you here. Here's the diagram. Now, this one's a little bit more complicated, so I'm going to try to show you from the picture instead of from the board. Again, notice this comes from S19 paper 13, number 6. And it asking you to find in terms of I, J, and K, and F. And the next one, it wants F to N. And the next one, M to N. And then you have a scalar product or dot product that uses what you found previously. So we're not going to get to dot product until the next video, but we want to be able to accurately find these I, J, and K component representations of these vectors so that you can apply it correctly. So here we have this interesting looking diagram here, and it says the diagram shows a solid figure A, B, C, D, E, F with a horizontal base, the ABC. So in other words, the ABC, this triangle is flat on the ground. And it's a right angled triangle. So right here at the corner is a right angle at the A, or kind of like at the origin there, A. The lengths of AB and AC are 8 units and 4 units respectively. So here you see AB with the 8 and AC with the 4. M is the midpoint of AB, so that means it's 4 on each side. And the point D is 7 units vertical above A. Triangle DEF lies in a horizontal plane with DE and DF and FE are parallel to our AB, AC, and CB. So this is directly above here, right in the corner, directly above it, parallel to the base. And then the lengths of DE and DF are 4 and 2 respectively. Unit vectors I, J, and K are parallel to AB, AC, and AD respectively, meaning these I, J, and K are right on these lines. Now, find MF in terms of I, J, and K. So we're starting here at M, and we're going to F, which is this far corner back here. Okay, so M to F. Now, remember you do it one variable at a time, I, J, and K. So let's start with I. M is halfway across. That means it's 4 away from the origin, and we need to go backwards to get here. Now this A is our corner, and it's right here with the D. And notice this is at a 90-degree with the J axis. Remember it said this A here is a 90, it's a right triangle. So that means this C and F are not actually going further back on the I axis. It kind of looks like it is, but it's not, because this is a 90-degree here. So from M to A is the same thing as from M to D as far as the I axis goes. Okay, remember we're only talking about I axis right now. So from M to A, the same thing as from M to D, same thing as M to F, because this is perpendicular here. So it doesn't move out more on the I axis. It just goes into the board or into the computer there. Okay, so we're only going back 4. So you have a minus 4i, minus 4i. Now for the J part, notice the J part, this is parallel here. So from the corner, it's just going 2 along the J. Notice C is further out, it's 4 out. F is only 2 out along the J. So far we got minus 4i plus 2j. Now we need the Z component And of course, it's going up 7 because it's going from the bottom all the way to the top. So minus 4i plus 2j plus 7k. Minus 4 plus 2 plus 7. That's MF. Now, the next one says to find F to N. F to N is this one right here. So how far is that along the I-axis? Well, notice the total I is 8, but DE is 4, and N is halfway along. It's the midpoint of FE. So N would only be 2 units along the I-axis. So here's 8, here's 4, and half of that is 2. Remember, this is perpendicular here. So F is not actually back, it's just into the screen. So over 2 on the I-axis, so plus 2i. Now we have to go backwards along the J, because remember F was 2 along the J, and we have to come back to N, which is halfway, so it's minus I. Okay, so over 2 on the I, minus 1 on the J, and then F and N are both at the top of this diagram, so there's no change in the vertical direction. So you don't have a K value. You don't have to put 0K, you just leave it blank. So you have 2I minus J. Then the third one wants you to find MN from M to N. Here's M, and we're going to N, from M to N. So this one, remember M is half of 8, which is 4. N is half of 4, which is 2. So we're going backwards from M to N. We're going before, and then minus the 2 gives us 2 more. So we have to go minus 2i, minus 2i. N was only 1jn because F is 2j, so that means N is just 1j. M is at the front, so we have to go along the j axis plus 1. And then we're going all the way from the bottom all the way to the top, so plus 7k. So negative 2i, a plus 7k, and a plus 1j, but put it in alphabetical order. So it's actually minus 2i plus 1j plus 7k. So let's go to the board just so that you can see. I put the answers here in case you want to write down these answers and then think it through again yourself. You can write these answers down and go back to the diagram and try to think it through. But very important that you get those down because again, it's going to carry into the next part of the question. So I'll set up one more for us. Okay, here's our last example for this video. Let's go take a look at it. Here again is a 3-dimensional diagram. The diagram shows this 3-dimensional shape, O, A, B, C, D, E, F, G. The base and the upper surface are horizontal rectangles. The parallelogram OAED and CBFG both lie in vertical planes. Point P and Q are the midpoints of OD and GF respectively. Unit vectors I and J are parallel to OA and OC respectively, and the unit vector K is vertically upwards. The position vectors of A, C, and D, so notice here our vocabulary position vectors from the origin. A, C, and D are given by OA as 6, OC is 8, and OD is 2i plus 10k. So notice OA is 6, OC is 8, and OD is over 2 and up 10. So the vertical part is 10. So we have 6, 8, and 10 are the sides that we're working with. Express each of the vectors PB and PQ in terms of I, J, and K. So again, we're going to do that here in the diagram instead of drawing it on the board. Their diagram is better than what I can draw. So from P to B, we're going here all the way down over to here. So notice P has been shifted over from the straight vertical, means it's leaning into this I vector here. So this is 8 across, but D is already 2 units over 2I. Okay, so 2 units over, and P is half of that. So it's already 1 unit over. And so we're going from 1 unit over all the way to the end. B is right along this J-axis, so it's not any further out on the I-axis than what A is. It's only further into the screen there. And so A and B are both at 8. P is at a positive 1. So from 1 to 8 would be 7. Here. And just a second. Okay, I was looking at the wrong number here. So notice OA is 6. I was saying 8, but that's OC. Sorry, we have 6. 6 from O to A. So 6 over A and B are both at the 6 mark. P is over 1. So from 1 to 6 is 5. I was looking at the number 8 when I got 7. So it's the number 6. O to A is 6. And then minus the 1 gives us from P to B then is 5. So 5I. And then J is 8 because P is at the front. And we're going the full length along J, which is 8. So 5 on the I plus 8 on the J. And then P is halfway up, and this is a 10 high. So P is at 5, and we're going down. So remember to put the negative on it. We're going from P to B, we're going down 5 units of height. So P to B is over 5 on the I, in 8 plus 8J, and then down 5 or minus 5K. Second part says to find from P to Q. So from P to Q, again, remember that P is 1 unit in, so it's starting at the 1. G is starting at the 2. It's leaning all the way over. And remember, D and G are at the same point on the I-axis. And remember, it was over 2I. So G is at the 2, and Q is halfway between G and F. So G and F are 6 units long. So G to Q would be 3, and P to G would be 1. So remember, P is over 1, but D is at 2. So from 1 to 2 is 1, and then plus the 3 would make 4. So we have a positive 4I from P to the Q is 4I. P is at the front, Q is at the back, so again, plus 8J. And now we're going up from P to Q. P is halfway of the 10, so it's 5. Going all the way up to 10 means a plus 5 on the K. So 4I plus 8J plus 5K. Let's go back to the board. Well, actually, I need to show you, I need to show you the second part of the question, which says determine whether P is near to Q or to B. Is P closer to B or to Q? So here we are at the board. Here's PB, 5I plus 8J minus 5K. Here's PQ, 4I plus 8J plus 5K. That is the directions on how to get from P to B and from P to Q. It's in component form. Now we want to answer the next part of the question because it deals with magnitude. So is P nearer, closer to B, or is it closer to Q? Well, in order to answer that, you have to know the distance. Distance is magnitude. So we just talked about magnitude earlier. So the magnitude from P to B is, and you use your distance formula with your 3 values. So you have 5 squared plus 8 squared plus a negative 5 squared. And of course, the negative will cancel out with the square. So we get 25 plus 64 plus 25 is the square root of 114, which is approximately 10.7. Then from P to Q, this distance, again, the magnitude of PQ is the square root of 4 squared plus 8 squared plus 5 squared, which gives us 16 plus 64 plus 25, which comes out to a square root of 105. And that comes out to approximately 10.2. So our answer is that P is closer to Q. P is closer to Q because the distance is shorter than it is to B. So there's our first of our videos for vectors, although it's part 2 because part 1 was iteration. And we will have a few more vectors. We still want to cover a few more things that are core to vectors, but at least this gets you to deal with 3-dimensional objects as well as magnitude, which is foundational for some of the other skill sets. So as always, thank you for joining me in the Zoom room and hope to see you again next time.